Sometimes, even the most practical questions need some fairly abstract mathematics to answer. Sometimes, in answering them, you are led to ideas that underlie a completely independent field of knowledge, where these ideas are studied for their beauty and power. Let's start with a concrete real-world problem, introduce some algebra, and see where it takes us. You've probably seen or even used a traditional scale before. It is a simple device for comparing the weights of two objects. It basically consists of a beam with a hinge in the middle which can rotate. You can hang two objects from the ends of the beam, and if they have the same weight, the beam stays horizontal. If not, it will tilt to the side of the heavier object. The usefulness of such a scale comes from the following equivalence. The beam is horizontal if and only if the weights are the same. In particular, if the scale is in balance, we know for sure the objects have equal weight. For this video, we might call this equivalence by the unnecessarily fancy name, the principle of unique balance. Now, what if we want to compare the weights of several objects at the same time? One idea would be to use regular polygons to generalize the traditional scale. For example, for three objects, we might use an equilateral triangle with a special hinge in its center that rotates in any direction. Intuitively, if we hang three objects of the same weight from the vertices, the triangle should stay horizontal. We can do the same with a square, a regular pentagon, a regular hexagon, and so on, and achieve balance by putting the same weight on all vertices, since the polygons are regular, so the weights are evenly distributed. But which of these satisfy our principle of unique balance? Take the square, for example. It might be intuitively clear to you that for the square to stay in balance, we only need that the opposite vertices have the same weight. For instance, we could hang one unit of mass from these two vertices and nothing from the others, and so the problem reduces to the scale with only two objects. So the square does not satisfy our principle. Yet, what about the triangle? What does your intuition tell you? You might be inclined to say that all weights must be equal for it to be balanced. And you would be right. You can try and prove this yourself directly. You might even have a hunch for what happens in general. You can pause the video for a minute to think about it. Maybe you made the important observation that there is a big family of polygons for which our principle does not work. Indeed, let n be the number of vertices of the polygon, so the number of objects that we are comparing. If n is a composite number, meaning that n is the product of two numbers n1 and n2 that are not 1, then a regular polygon with n vertices will contain a regular polygon with n1 vertices. So we can put equal weights on the smaller polygon and leave the rest of the vertices empty, and still achieve balance. So the principle does not hold. For simplicity, we will also talk about two diametrically opposite points as a regular polygon with two vertices, even though that's technically an abuse of language. So we are now left with the polygons with a prime number of vertices, n equals p for prime. We might guess that the principle of unique balance holds in this case, at least based on our examples with n equal to 2 and n equal to 3. But making a bold conjecture like this based on two examples is dangerous. Yet it turns out that our intuition is correct. In this video, we will see how we can properly prove that our conjecture is true using the tools of algebra. This might take a while, but we'll see important and beautiful ideas that I truly hope will give you some new perspectives on the mathematical knowledge you already have, and motivate you to further study complex numbers, the arithmetic of polynomials, number theory, and more. Let's begin by formalizing our setup. We will use two-dimensional vectors to describe the polygon. For simplicity, we put the center of the polygon at the origin of the plane, and then we denote each vertex by the corresponding vector v0, v1, v2, and so on. For later purposes, we start counting at 0. The vectors are all of equal length, say 1, and all of the angles between two neighboring vectors are equal. For the drawing, I randomly chose n equal to 6, but you should extrapolate to the general case. Now, if we assign weights mi to each vector vi, then the formula for the center of mass is literally a weighted average. You multiply each vector by its weight, sum them all up, and then divide by the sum of the weights. To achieve balance, the condition is that the center of mass coincides with a geometric center, that is the 0 vector. Because scaling the 0 vector by anything still gives the 0 vector, we arrive at this simpler condition. So, our conjecture now says the following. In the case of prime numbers, if the sum of weighted vectors is 0, then all the weights or coefficients should be equal. For simplicity, we will assume that the weights are non-negative integers, at least with respect to some unit of measurement. Now, the first major idea in tackling this problem is to introduce complex numbers. Maybe that sounds like it came from nowhere, but recall that complex numbers are two-dimensional numbers, which is quite fitting for a two-dimensional problem. More precisely, a point with coordinates x and y in the plane is represented by the number x plus iy. Another way to describe complex numbers is by using polar coordinates. So I can tell you the distance between the point and the origin, and the angle between the vector and the OX semi-axis, and you can locate the point. In the language of complex numbers, we could write this as x plus iy equals r times e to the I phi, where phi is measured in radians. So let's describe the vertices of the polygon by complex numbers. By our assumption, the vertices all have distance 1 from the origin, so r is always 1. Each of the angles between vectors is 360 degrees over n, which is 2 pi over n in radians. So the vertex v0 can be described by the number 1 times e to the I times 0, which is just 1. And similarly, vertex v1 is 1 times e to the 2 pi I over n. Vertex v2 is 1 times e to the 2 times 2 pi I over n, and so on, simply raising e to the corresponding multiple of 2 pi I over n. One of the special powers of complex numbers, as opposed to just vectors, is, as trivial as that might sound, that you can multiply them. If you recall the multiplication property of the exponential function, turning a product into a sum, then you might notice that the square of the complex number representing v1 is equal to the number representing v2. More generally, vertex vk corresponds to the kth power of v1 as a complex number. Mathematicians usually denote v1 as a complex number by zeta, and write all of the other vertices as powers of zeta. Note how 1 is either zeta to the power of 0 or zeta to the power of n, going around full circle, since e to the 2 pi I is 1. In fact, these numbers are called the nth roots of unity, because they are the n solutions of the equation x to the n equals 1. For example, if n is 2, then the two square roots of 1 are 1 and minus 1. If n is 3, the only real third root of 1 is 1, since minus 1 to the third is minus 1. But over the complex numbers, there are two other roots, zeta and zeta squared. The roots of unity are useful in many areas of mathematics, especially in algebraic number theory, where they played a crucial role in the history and proofs of famous theorems such as Fermat's last theorem, proved by Andrew Wiles, and Catalan's conjecture, proved by Preda-Mihailescu. The way roots of unity are going to help us is by turning our problem about sums of vectors into a problem about polynomials. Since each vertex is represented by a power of zeta, we can write our balance condition using a polynomial in zeta. So we are trying to prove that if zeta is the zero of a polynomial with integer coefficients, then all coefficients must be equal. In other words, such a polynomial should be of the form c times 1 plus x squared and so on plus x to the power of p minus 1 for some positive integer c. This last polynomial, which we denote by capital Phi subscript p, has a name. It's called the pth cyclotomic polynomial. The name comes from Greek and means dividing the circle, since zeta is a root of phi, as we will see, and all the powers of zeta divide the unit circle into equal parts. Well, now we turned our original problem with weights and polygons into a problem about complex numbers and polynomials. Isn't this making it more complicated? Maybe, but more complicated in our case also means more structure. For example, let's see how we can instantly obtain a proof for what our intuition was telling us at the beginning. Namely, if we place equal weights on the vertices of the polygon, we should achieve balance. This is, after all, part of what we're trying to prove, so let's do a reality check. If all the weights are equal, then the polynomial in the balance condition turns into a constant multiple of the cyclotomic polynomial. To see why zeta is a zero of this polynomial, you might recognize this expression as a geometric series, which can be rewritten in the neat form zeta to the p minus 1 over zeta minus 1. Zeta is not 1, so this expression makes sense, but zeta is one of the complex pth roots of unity, meaning that zeta to the p is 1. So this quotient is 0, which is what the balance condition requires, proving our intuition right. It seems we're on the right track here. To go further, we need to dig deeper into polynomials and their arithmetic. One of the basic properties of a polynomial is its degree, which is the highest power of x appearing with a non-zero coefficient. The polynomials that interest us, the ones in our conjecture, might have degree p minus 1 or lower, depending on which coefficients or which weights are 0. So if we want to prove that f must be a constant times the cyclotomic polynomial phi, which has degree p minus 1, then we should at least be able to show that if f is not the zero polynomial, then f has degree p minus 1, the same as the cyclotomic polynomial. Let's look at some examples. For p equals 2, the degree of f is at most 1, and any polynomial of lower degree is constant. So if zeta is a zero of a constant polynomial, that constant must be 0. But we're really only interested in non-zero polynomials here. Or take p equals 3, and consider again polynomials of lower degree. We've seen what happens with constant polynomials, so the only other case is that of degree 1 polynomials, ax plus b, where a and b are integers and a is not 0. But if zeta is a zero of this polynomial, it would mean that zeta is a rational number. But in this case, zeta is a complex number with a non-vanishing imaginary part. So this is not possible at all. Now this starts to get tricky for larger primes p. What should we do in general? A good trick that every mathematician learns at some point is, if you have a set of objects that are not given explicitly, or you just don't understand well yet, look at objects that maximize or minimize some property. That way we artificially inject some extra properties that might come in handy. In our case, we could minimize the degree, so out of all non-zero polynomials with integer coefficients that have zeta as a 0, take one polynomial that has the lowest possible degree. We call it m for minimal. Now we have two polynomials, phi and m, and We're not really sure what m is, but it has minimal degree, and the conjecture tells us that it should actually be a constant times phi. But how can we put these two polynomials and their properties together to prove our conjecture? This is where polynomial arithmetic comes into play. We use the word arithmetic here because, really, polynomials often behave as if they were integers. You can add and multiply them together, but most importantly for us, we can divide them. More precisely, we can perform Euclidean division, or division with remainder. Just like in the case of numbers, recall that if f and g are two polynomials with, say, rational coefficients, then we can write f as a product of g and another polynomial q, the quotient, but the division might leave a remainder. To make this a good approximation to f by a polynomial multiple of g, the remainder, which you can think of as the error in our approximation, should be as small as possible. For polynomials, the right thing to ask for here is that the degree of r should be smaller than that of g. Now let's go back to our problem and see what happens if we divide phi by m. This is a classical argument. We get a quotient polynomial q and a remainder r. If we evaluate this identity at zeta, we see that these two terms are 0, forcing r of zeta to also be 0. But r has a lower degree than m, which we took as having minimal degree. This can only happen if r is the zero polynomial. So really our minimal polynomial must properly divide phi. We now need the final idea of this video, which is that of irreducible polynomials. This again is an instance of polynomials behaving like numbers. Just as integers are composite or prime, polynomials can be reducible or irreducible, depending on whether you can write them as a non-trivial product of two other polynomials. By non-trivial here we mean roughly that neither of the polynomials is a constant. The question of reducibility really depends on the kinds of polynomials you allow in your product. For example, if you allow polynomials with complex coefficients, then in fact all polynomials with degree higher than 1 are reducible. Indeed, one of the consequences of the fundamental theorem of algebra is that all polynomials factor into polynomials of degree 1 with complex coefficients. What happens if you allow only polynomials with real coefficients? It turns out that in this case, any polynomial of degree higher than 2 is reducible. You might try to prove this yourself. For this, you might want to use the fundamental theorem of algebra and complex conjugation. Now, polynomials with rational coefficients are much harder to classify. In fact, for any number n, there is at least one polynomial with rational coefficients and degree n that is irreducible over the rational numbers, that is, only allowing polynomials with rational coefficients. One example relevant to us is our cyclotomic polynomial. It was Gauss who first proved that phi p cannot be written as the product of two other non-constant polynomials with rational coefficients. The proof uses clever tools such as Gauss's lemma for irreducible polynomials and Eisenstein's criterion, which can be proved using modular arithmetic. This will all be the topic of the next video. To finish the problem, let's recall that we managed to write phi p as the product of m and another polynomial q, both with rational coefficients. But Gauss tells us that the cyclotomic polynomial is irreducible, so one of these polynomials must be constant. But m cannot be constant since it is non-zero and zeta is a solution of m. It must therefore be q that is constant. Rewriting this slightly, we see that our minimal polynomial m is a constant times the cyclotomic polynomial phi. Finally, let's put everything together and recall the definition of m. We looked at all polynomials of degree at most p-1 that have zeta as a 0 and chose any one of those that has minimal degree. We prove that m is a constant multiple of the cyclotomic polynomial, so that the minimal degree actually equals p minus 1, the degree of phi. So if we take a polynomial like in our conjecture, its degree is at most p minus 1 and at least p minus 1 by what we've just shown. So it equals p minus 1. But recall, in choosing m, we could choose any polynomial with minimal degree. So everything we proved for m actually applies to our f as well, including the conclusion of our conjecture, which finally finishes the proof. Going back to the original problem, this means that the principle of unique balance that underlies the usefulness of the traditional scale also works if we are comparing the weights of a prime number of objects. For example, if a regular pentagon with weights on its vertices is balanced, then we can be certain that all weights are equal. Reaching the end of this video, I'd like to point out that this balancing problem is related to the so-called centrifuge problem, and although the precise details are slightly different, they both lead to the same ideas. But as already mentioned, roots of unity and cyclotomic polynomials have so many other applications, like the ancient problem of constructing shapes using straight edge and compass, elementary number theory, but also very advanced topics like class field theory. So I hope this video managed to convince you that polynomial division isn't just an annoying exercise you do in school, and that it encourages you to study more about all of these beautiful topics. This was my first maths video, and I'd like to thank Grant Sanderson from 3 Blue 1 Brown for organizing the Summer of Math exposition. If you're curious how to prove that the cyclotomic polynomial is irreducible, stick around for the next video.